Priority classes allow you to control which pods get scheduled first in resource-constrained Kubernetes clusters. When your cluster is running low on resources, priority becomes critical for ensuring that your most important workloads continue running, while less critical ones may be delayed or preempted. This scheduling mechanism helps maintain the stability and availability of mission-critical applications. Pod priority indicates the importance of a pod relative to other pods in the cluster. Higher priority pods are scheduled before lower priority pods, ensuring that critical workloads get resources first. When resources become scarce, critical system pods can preempt lower priority pods, effectively evicting them to free up resources. This priority system is defined using priority class resources with integer values, where larger numbers represent higher priorities. To create a priority class, you use the scheduling.k8s.io/v1 API version with the kind set to priority class. The metadata name field specifies the name you'll reference later, such as high-priority. The value field contains an integer representing the priority level, like 1 million. The global default field, set to false in most cases, determines whether this becomes the default priority for pods without a specified priority class. Finally, the description field provides human-readable context about when to use this priority class. Let's break down the key fields in a priority class. The value field is an integer that determines the priority level, where higher numbers mean more importance. The global default field, when set to true, makes this the default priority for any pods that don't explicitly specify a priority class. The description field contains a human-readable explanation that helps cluster users understand when they should use this particular priority class. These fields work together to create a clear priority hierarchy in your cluster. To assign a priority to a pod, you add the priority class name field to the pod specification. In this example, we have a pod named critical-app that uses the high-priority class we created earlier. The spec section includes the priority class name field set to high-priority, which tells Kubernetes to apply that priority level to this pod. The rest of the pod specification remains normal, with containers defined as usual. This simple addition ensures your pod gets the scheduling priority you need. Preemption allows high-priority pods to evict lower-priority pods when resources are insufficient. Here's how it works. The scheduler first identifies lower-priority pods that can be removed to make room for the high-priority pod. Those preempted pods then receive a graceful termination period, typically 30 seconds, to shut down cleanly. Once the resources are freed up, the high-priority pod is scheduled on that node. This mechanism ensures that critical workloads can always find resources, even in a fully utilized cluster. You can control whether a priority class allows preemption using the preemption policy field. In this example, we create a priority class named no-preemption with a value of 1000. The preemption policy is set to never, which means pods using this priority class will have high priority for scheduling, but won't preempt other running pods. This is useful for workloads that need priority, but shouldn't disrupt existing pods, such as data science jobs or batch processing tasks that can wait for resources to become naturally available. When working with pod priorities, follow these best practices. First, reserve high priorities only for truly critical system components to avoid unnecessary preemptions. Second, use descriptive names and clear documentation for each priority class so that teams understand when to use them. Third, establish priority tiers across teams to prevent conflicts and ensure consistent priority assignments. Finally, monitor preemption events regularly to verify that the system behaves as expected and adjust your priority strategy as needed. Following these practices helps maintain cluster stability while ensuring critical workloads receive the resources they need.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.